Hi everyone, so just want to give a short recap on waves and light before you all sit for your actual WA1 exams, and just 10 or 15-minute recap of the key concepts before you all do your actual practices yourself. Right, so without further ado, let's go straight into the recap. First thing I want to recap is loudness and pitch. So for sound waves, we gotta know that the loudness of a sound wave affects the amplitude, and the pitch of a sound wave affects the frequency, right? So in the exam, what they'll do is they'll give you a wave like this and they'll say, draw a sound wave with, for example, 2x the loudness and 2x the pitch, right? So how do we do this? The first thing we gotta understand is that 2x the loudness means 2x the amplitude. So if right now this one is the amplitude, right? Amplitude is the distance from the equilibrium to the maximum point. Right now, this one is the amplitude. 2x amplitude looks something like this, right? It'll be 2 times higher. So it will be like this. That's the first thing. Second thing is that 2x the pitch means that you gotta realize it means that 2x the frequency, right? Because pitch affects the frequency. And by the formula, frequency equals to 1 over period. What you can see is that if you actually 2x the frequency, it means that the period of the wave is actually half, right? So right now, this one is the period. This is the time taken for one full wave. And if we halve the period, now one full wave just takes this amount of time. This one is half the period, right? So the new wave will look something like this. It will be 2 times the amplitude, but it will be half the period. Right, so that's the first part of sound waves, is loudness and pitch. This is the more straightforward part of sound waves. Now, the next part is echo, right? And basically, echo, there's 2 steps. First step is you want to draw the path of the sound wave. This is just to make it easier, and I always recommend my students always draw the path of the sound wave just to make it easier, right? So if you shout into a wall, for example, we know that the sound wave is gonna travel like this. Gonna go here, and it's going to actually echo and bounce backwards. So that's the first thing. Very clearly draw how does the sound wave travel. So over here, sound wave travels here and comes back over here. Now, step 2 is you want to use speed of sound wave equals to distance over time, right? But take note, this distance is what? This distance must be the total distance traveled by sound wave, right? So usually the trick in the exam is that they will give you, for example, they'll say that this distance is d, right? But what you gotta understand is that the sound wave actually goes here, then it bounces back. So the total distance that is traveled by the sound wave is actually 2d, right? Or let me just give a number example. Let's say they say that this distance is 300 meters. Then the d that you put over here is actually 600 meters, right? Because the sound wave over here actually traveled 300 here and 300 back. Total is 600 meters. So in fact, let's try to use this into a real example question below. Right, over here, feel free to pause the video and try the question yourself first. Basically, over here, John is shouting in front of a building. So the moment John shouts, he actually emits sound waves into both directions at the same time, right? So the moment he shouts, he emits a sound wave to the right side, and at the same time, he also emits a sound wave to the left side. So both directions at the same time, this sound wave is gonna get echoed and go back to bed. Right, first step is we draw the path of the sound wave. So over here, when the blue color sound wave reaches, that's the first shout, and the second shout is when the red color sound wave reaches. That's why Ben over here hears 2 shouts, right? Then we want to find the speed of the sound wave. So what we want to do is, we realize that over here, when the blue color sound wave reaches Ben, the blue color sound wave actually traveled a distance of 750 meters, right? Means that the red color sound wave must have also traveled a distance of 750 meters. right? The moment the blue color sound wave reaches band, it means that the red sound wave at that instance already traveled 750 meters as well, right? So if over here is 300 meters, it means that over here, this distance is actually 450 meters, right? Just when the blue sound wave reaches. And so the extra distance that the red sound wave must travel so as for Ben to hear the second shout is actually 750 plus 300, so that's 1050 minus 450. This extra distance is actually 600 meters, right? So the idea is that when the first sound wave reaches, that's the first shout, the second sound wave traveled 600 meters of distance in 2 seconds. Then the second shout is being heard. So now we know the speed, we know now we can calculate the speed using speed of the sound wave equals to distance traveled by the sound wave over the time taken, which is 600 meters over 2 equals to 300 meters per second. Right, and that's the answer for this question. So for sound waves, just go and draw the path of the sound wave and use the formula speed equals to distance over time. Right, so that's a recap for sound waves. Now we move on into light. Right, light is a very, very big topic, but let's try to recap it in this video. So first thing is reflection. Reflection is quite simple. You just got to know that angle of incidence equal to angle of reflection. Right, so if we have a light wave over here, a mirror over here, and the light ray bounces like this, basically the idea is that the angle of incidence equal to angle of reflection. Right, these two angles are equal. This one quite straightforward. Now, second thing is that refraction. Right, this one is the more complicated one. There are three main formulas for refraction. The first one is N equals to C over V. Right, N stands for refractive index. So N stands for refractive index. C stands for speed of light in vacuum. And this is a number that you gotta memorize. So speed of light in vacuum is actually 3 times 10 to the power of 8 meters per second. Right, and finally V stands for the speed of light in medium. Right, so N equals to C over V is the first formula. Second formula is N equals to sine I over sine R. Right, whereas I actually refers to the angle in air. I is always the bigger angle, right? It's always the angle in the air, whereas R is the angle in the medium. Right, and finally the last formula is N equals to 1 over sine C. Right, just take note, this C is different from this C. This C is the speed of light in vacuum, whereas this C is the critical angle. Right, so just don't go and mix up these two things. This C stands for the critical angle. Right, so these are three main formulas for refraction that you gotta know. One important thing is that all angles are always measured from the normal. Right, this one is a very, very important concept in light. Because what the examiner will do, for example, if we have, let's say, two mediums over here, right? Let's say light is traveling like this. The examiner, what they will do is that they'll tell you that this angle over here is 50 degrees, right? But what you gotta know is that the angle, like whatever angle of incidence, angle of reflection, angle of refraction, critical angle, right? Everything is always measured from the normal. So over here, your angle of incidence is actually 40 degrees, right? Because it's measured from the normal. This is your angle of incidence, not 50 degrees. Okay, so just take note of that. Next we move into optically denser versus less dense medium. Right, what's the difference between optically denser, so short form, more dense, versus a less dense medium? The first difference is obviously more dense medium has a higher refractive index. whereas a less dense medium has a lower refractive index, right? So more dense medium, for example, n equals to 3 and n equals to 2, right? The 3 is considered to be higher refractive index. It's a optically denser medium, right? The second difference is that optically denser medium actually bends towards the normal, right? When you enter a more dense medium, you're actually bending towards the normal. But when you enter a less dense medium, you're actually bending away from normal. Now, what's bending towards and away from the normal, right? A lot of students always mix up these two things, and I want to make this very clear to you all. So over here, the idea is that, let's say we have air and glass, right? We know that when we go from air into glass, air is less dense than glass, right? Or rather, glass is more dense than air. So if we go like this, what we know is that when light enters from air into glass, it will actually bend like this. Originally, the light ray was supposed to travel in a straight line, right? But the idea is that the light ray actually bend. When the light ray enters a more dense medium, it actually bend like this, closer towards the normal, right? This one is the normal and it's bending towards the normal. So that's what we mean by bending towards the normal, right? Same thing if we go from glass into air. Originally, it was supposed to go in a straight line, right? But what's happening is that the light ray is actually entering a less dense medium, which is air. So it will actually bend like this, right? It will bend like this because over here is the normal and it's bending away from the normal, right? So that's what bend towards the normal and bend away from the normal actually mean. Now, the last difference is that more dense medium actually light travels slower, and less dense medium light travels faster, right? That's the last difference between the two. So just important to memorize the three main differences between more dense and less dense medium. Now, another very important concept in light is that the bigger difference in density, the more you will bend, right? So let me give you an example over here. If let's say over here n equals to 1, and n equals to 1, n equals to 2, n equals to 1, and n equals to 3. Right, we know that when we're entering from a less dense medium to a more dense medium, what's going to happen is that, let's say like this, it's going to bend towards the normal, right? Less dense to more dense means that it will bend towards the normal. But now if you go from a less dense to an even more dense medium, you will actually bend even more towards the normal, like this. Right, the light ray is actually bending more towards the normal because over here there is a bigger difference in the density of the medium, right? Same thing if you go from, let's say, n equals to 1, n equals to 2, n equals to 1, n equals to 3, right? Again, n is the refractive index lah. So over here the refractive index is 3 and 1, right? So when you go from a more dense to a less dense medium, let's say like this, more dense to less dense, you are going to bend away from the normal, right? More dense to less dense means that you actually bend away from the normal. But if you go from a even more dense medium to a less dense medium, what you notice is that over here, the difference in the optical density is bigger, right? So it's actually going to bend even more away from the normal. It will bend even more away from the normal, right? So the idea is that the bigger the difference in density, it will always bend more. Doesn't matter if it's towards the normal or away from the normal, right? So that's for refraction. Next concept is total internal reflection. So first thing is the two conditions for total internal reflection. The first one is you must be traveling from a optically denser to a optically less dense medium. Right, total internal reflection can only happen from more dense to less dense medium. Cannot happen the other way around. So from less dense to more dense, there will never be total internal reflection. Right? The second point is that the angle of incidence must be bigger than the critical angle, then total internal reflection can happen. Right? So the main concept is that whenever light enters into a different medium, there's two things that can occur. So over here, for example, air, glass, air, glass, right? If light is traveling from glass into air, right, from a more dense to a less dense medium, the first scenario is that if the angle of incidence is less than the critical angle, what's going to happen is just normal refraction. Right? Because we know that for total internal reflection must be more than the critical angle. So if it's less than the critical angle, what's going to happen is that the light is just going to bend normally like this. Right? It's just going to bend away from the normal refraction. But if the angle of incidence is more than the critical angle, that's when total internal reflection happens. So over here, if this angle, so over here was the angle of incidence, less than the critical angle. Now if the angle of incidence is more than the critical angle, it will actually undergo total internal reflection. Right, the entire light ray will be completely reflected inside the glass. So these are the two scenarios. And usually in the exam, you have to calculate what is the angle of incidence and also the critical angle. So they'll say, explain or like predict what's going to happen to the light ray, right? And you got to see, is it less than the critical angle or is it more than the critical angle? And then explain like, therefore, what will happen, right? So that's the second concept. The fourth concept is image properties. And this one is just a lot of memory, but I summarize it into this table for you, right? So the idea is that wherever you place the image, right? I mean, whenever you place the object, the image properties will be different every time, right? If you place the object over here, the image will be different. If you place the object over here, the image will be different as well, right? So the way to quickly memorize the image properties is, first thing you gotta understand is that less than the focal length, the image will be virtual, and more than the focal length, the image will be a real image. That's the first thing. Second thing is that if you place the object exactly at 2f, the image will be the same size. So if you place the object over here, the image will be the same size over here, right? If you move the object to the left, the image will be smaller. If you move the object closer to the focal point, the image will be bigger. And that's pretty much all the image properties that you gotta know summarized into this cheat sheet over here. Right, so that's for image properties. The next thing is lens diagrams. How to draw any lens diagrams is just 3 basic steps, guys. The first step is to draw a straight line through the center, right? So by the way, over here is a real image, right? Costs more than f. Over here is a virtual image since it's less than f. So the first step is you want to draw a straight line through the center of the lens like this. That's the first step. Second step is you want to draw a horizontal line which will then bend through the focal point. Right, so first step. Second step is you want to draw a horizontal line like this, which then bends and passes through the focal point like this. So this is step 2. Right, and for real image, there's just 2 steps. So you see the point where the 2 light rays meet. This will be your real image. Right, and of course, remember to add your arrows. So for real image, there's just 2 steps. For virtual image, it's the same first 2 steps, but the third step is a bit different. So for virtual image, So step 1, you draw a straight line through the center. Step 1 is the same step like this. Step 2 is also the same. You draw a horizontal line which then bends and passes through F, like this, right? But virtual image, there's an extra third step. Virtual image, you want to extend the dotted lines backwards, right? So actually these two lines, you want to actually extend them backwards like this. Of course, use your ruler, extend them backwards, and basically the point where the two lines meet, that will be your virtual image. This one will be your virtual image, right? So for virtual image, it's just 3 steps. And as you can see, the first 2 steps are the same for real and virtual image. So kind of straightforward, right? As long as you just memorize these 3 steps. Now, the last one is mirror drawings, right? Mirror drawings is just 3 simple steps. First step is you want to draw the image on other side of mirror, right? So over here, this one is your eye, and this one is the object, and this one is the mirror. The first step is to always draw the image of the object on the other side of the mirror. So over here, this is roughly 3.5 cm. The image of the object will always be equidistant, so also 3.5 cm on the other side of the mirror. So this one will be your image, right? Step 2 is to draw a straight line from the eye to the image. So step 2 is you want to take a ruler, you want to draw a straight line from the eye to the image using dotted lines inside the mirror, right? Because light cannot travel inside the mirror, it just gets reflected. So that's the second step. The third step, the final step, is to connect object to point. Okay, what do I mean by point? Basically point, I mean this point over here, where the light ray strikes the mirror. You want to take your ruler and connect the object to this point, like this, right? And that's the 3 steps. Okay, of course, remember to add your arrows. So at the end, the arrows must always go into the eye. And yeah, that's the 3 steps to draw mirror diagrams, right? So that's just a very brief summary of all the concepts that you need to know for sound waves and light. And I hope that that helps you in your WA1 revision. Right, so as usual, I'm Ting from the A1 Physics, and if you're interested in getting tutored by me, joining my physics classes, just go and WhatsApp the number around the screen and I'll send over to you the details. Alright, see you in the next video.